Hello everyone and welcome in today's video. As on the previous examples, today we are continuing again with the force method where we have this L-shaped frame for which according to the exercise we have to find the bending moment at point B. For member AB there is a distributed load which is acting on it and we have the given dimensions of the members and also the flexural rigidity for the members is assumed to be constant. At point A we have a fixed support and at point C we have a roller support. So without any further ado, let's just start solving by hand the given example with the force method. And the first thing to be done, at least what I prefer always, is to determine the degree of indeterminacy of the structures. So as we know from the roller on point C, we're going to have one reaction and we are going to have three reactions at support A since we have a fixed support at this point. As we already know, we have three equilibrium equations and if we do the difference, 4 minus 3 is going to be 1. Therefore, the degree of indeterminacy for this structure is 1. To use the force method, I decided to release the bending moment at point B as that's what was asked from the exercise to find. And after we introduce an internal hinge here, then the structure is going to become statically determinate. And then we have to take into account also case 1 for which we apply that virtual bending moment at this point. So now let's just start to solve for case 0 as now we induced an internal hinge at point B. Now the structure is going to become statically determinate and for that we start to take sum of forces on y direction, therefore we can define the value of A0. And also analyzing member AB separately and taking sum of bending moments equal to 0 at the internal hinge, basically at point B, then we are going to have the following equation. Therefore, we can determine the value of this M0 here, as we already know that at the hinge, the bending moment is 0. So this is going to be the bending moment coming for case 0 at support A. And then we take the sum of bending moment at point C equal to 0 to this point for the whole frame now. And in that way, we are going to determine A01, this one, which is going to be 0. Taking the sum of forces on X, we got that C01 is going to be again 0 as no horizontal load is acting on the structure. To use or to apply the force method, we also need to define the bending moment functions where we do have discontinuities on the beam. And I started from the bottom from point C and I took this S distance and this is the cut section where I decided to go. Then we take the sum of bending moments at this cut and the bending moment is going to be 0. Next, I decided to take the cut continuing to the next discontinuity and taking the bending moment at the cut, and this is going to be the equation which I have. As a cross check, we can take the bending moment at 0, which is going to be here, and it's going to be obviously 0 as we already induced an internal hinge at this point. We can try to do the bending moment at 2a distance, and if we substitute that there, we are going to get that the bending moment at distance 2a is going to be 2qa squared. And let's check what we got from this m0, which is basically this bending moment at this point. This m0 is going to be 2qa squared. So our bending moment functions are correct. Now we jump on case 1, and again, as mentioned before, the structure is statically determined as we induce this internal hinge there, and we take sum of forces on y, and we find the value of A1, which is going to be 0, and analyzing the member AB separately and taking sum of bending moment at this hinge, we know that at this hinge the bending moment is 0, but we induced this bending moment, therefore we need to take into account this virtual bending moment with value 1 kilonewton meters. And we get that this bending moment here is going to be minus 1 kilonewton. Considering the whole system, we are going to take the bending moment at point C, and then we're going to find the value of A11, which is going to be minus 1 over A. Again, we take sum of forces on X, and we find this value of C11 as 1 over A. Now, as mentioned before, to apply the force method, we need to find the bending moment functions, and again, utilizing the cuts where we do have discontinuity on the frame, we find the bending moment function. So I decided to take the first cut from here, and then this is going to be the bending moment which we have. Then next, I will apply the cut at this point, and take the sum of bending moment at the cut equal to 0 and define the value of this m1. So This should be M1. There is a small typo here. Next, we take the summary of results. For case 0, these are going to be the bending moment functions for the given boundaries. And the same for case 1, we have these bending moment functions for the given boundaries. Next, we apply the force method as on the other videos. And applying the compatibility, we can find that our unknown is going to look like this. Therefore, we need to find these two unknowns. And now we apply the integrals all over the frame, which is at point A, B, and C, all over these points. And we take the bending moment functions integral as shown here, and we are going to find this unknown as follows here. We continue to do the same thing for case 1, which is the virtual case, if we can call it like that, and we find the unknown which we are looking for. Then our unknown x1, which basically is the bending moment at point B, if we take the division of these two unknowns which we already found, this is going to be the bending moment at point B. As a cross-check, if for example we assume that this dead load which is acting on member AB is 10 kilonewtons and this distance A is going to be 5 meters, the bending moment is going to be as follows: 142.85 kilonewton meters. And of course, as a good cross-check is to model the frame in a finite element method software, and as we see here, we have done that and the result is correct, which says that our hand calculations are correct and we can use this formula in the future if it's needed. This wraps up the video for today. I really hope you enjoyed today's video. Thank you very much for your time. Do not forget to like, share, and subscribe to our channel. If there is any questions, leave them down in the comment section below. See you on the next video.